In the mid-1940s, conventional aircraft required tail structures for stability. Dragging these vertical and horizontal surfaces through the air created a severe aerodynamic drag penalty. The Horten HO 229 eliminated these structures entirely. By unifying the fuselage and wings into a single flying wing architecture, engineers aimed to minimize parasitic drag and maximize forward speed. This design resulted in a wingspan of 55 feet 1 inch and a total wing area of 557 square feet. Its smooth, curved profile led to historical rumors that the shape was engineered specifically to defeat early radar systems. However, tests conducted by Northrop Grumman in 2008 demonstrated that the design lacked effective radar-absorbing properties by modern definitions. The engineering focused on aerodynamic efficiency and lift optimization rather than a stealth-based radio frequency design. Removing the tail to gain efficiency introduces an immediate crisis in flight control. A standard empennage, the vertical and horizontal stabilizers, acts like the feathers on an arrow, keeping the aircraft in steady flight. Without a vertical stabilizer, an aircraft becomes highly susceptible to side slipping. A crosswind can push the rear of the aircraft out of alignment with its forward momentum. If unchecked, this side slip degrades into a flat spin, stripping the aircraft of forward lift. To prevent this, German engineers attempted to control pitch, roll, and yaw through a series of mechanical linkages along the trailing edge of the wing. This is a B-2 Spirit bomber. It solves the same aerodynamic problem using fly-by-wire computers that make thousands of micro-adjustments per second to stay airborne. The HO 229 represents an analog attempt at a digital-era problem, relying on physical mechanics to perform the work of microprocessors. The physical construction of the aircraft was dictated by the material shortages of late-war Germany. The airframe consisted of a steel core wrapped in varying thicknesses of European beech veneer plywood, attached using wooden spacers to form the aerodynamic profile. Enclosing jet engines in wood presented a fire hazard. To stop sparks igniting the airframe, the plywood was coated in a fire-repellent green paint. This archival image shows the primary power plant, the Junkers 004B2 Jumo jet engine. Two of these units were embedded directly into the wooden frame. Air entered the front section, was compressed by an 8-stage axial compressor, and fed into combustion chambers where it mixed with fuel and ignited. Each engine produced 2,000 pounds of thrust. They were protected by metal intake cowlings hammered over the leading edge to shield the surrounding wood. By this stage of the war, Germany could no longer source the high-quality, heat-resistant alloys required for reliable jet performance. Using lower-quality steel in the engine turbines caused rapid thermal degradation during high-speed operations. These compromises limited the aircraft's combat viability, reducing the engine's service life to approximately 20 hours. To maneuver this lifting surface, the engineers relied entirely on the trailing edge of the wing to manage pitch and roll. These surfaces, called elevons, combine the functions of traditional elevators and ailerons near the wingtips. Pitch is controlled by moving them in unison. Both up raises the nose, both down drops it. Roll is controlled by actuating them in opposite directions, forcing the aircraft to bank. To assist with stability, the wings were built with a 4-degree dihedral angle, sloping upward from the central fuselage to the tips. This specific dihedral geometry passively increased lateral stability, helping the flying wing naturally correct its balance during a roll. While elevons managed 2 dimensions of flight, they left the yaw axis entirely unmanaged. Without a vertical rudder, lateral instability remained a constant danger at high speeds. The solution was the drag rudder, which operated in pairs near the wingtips. Deploying a drag rudder on one side creates localized air resistance. This pulls that wing backward and forcefully snaps the nose into a new heading. Spoilers provided secondary drag management, essential for stability at high speeds and managing descents. Lifting a spoiler rapidly disrupts the airflow above and below the wing, intentionally decreasing lift and increasing drag during landing. Replacing a static tail with this matrix of sensitive drag surfaces made the aircraft difficult to fly without computer assistance. The pilot sat at the center of this control matrix. A curved canopy design was used to provide rearward visibility that would otherwise be blocked in a tailless design. The analog startup sequence was complex. The pilot held a priming button while monitoring a tachometer to spin the turbines to the necessary speed. Ignition occurred at 800 RPM. At 1800 RPM, the pilot activated the main switches to draw J2 synthetic fuel, made from brown coal, into the engines. Because Allied bombing campaigns frequently damaged German air bases, the aircraft was designed to operate from short, compromised runways. The massive wing area provided a low stall speed, allowing liftoff in just 3,600 feet. A drogue parachute was used to arrest the aircraft's momentum on those same short landing strips. Pilots managing this aircraft faced an immense workload, balancing volatile early jet engines and unstable aerodynamics entirely by hand. The jet's theoretical performance was significant, with a projected maximum speed of 607 miles per hour. This is an American P-51 Mustang. The HO-229 was designed to outpace conventional Allied propeller fighters like this one. To execute tight combat maneuvers at high speeds, the wooden airframe was reinforced to withstand an estimated 12.6 Gs in a dive. However, an aircraft built to withstand 12.6 Gs exceeds human physiological limits. A pilot would lose consciousness before the airframe reached its structural breaking point. The war concluded before the aircraft could be deployed. This archival image shows a captured prototype segment being transported by American forces for post-war research. The Horten HO-229 proved the feasibility of the flying wing concept, though the design preceded the digital fly-by-wire technology required to stabilize it.